target address, which is going to be A, and A was written in the previous instruction, the previous cycle, good, plus what we just said, the sign extent of bits 15 through 0, the immediate field. So now we have the address.
A or B that gets the sign?
Where?
Is it A or B that gets the sign?
This one you mean?
Yeah.
Yeah, that's A. Yeah, if you look at the machine code, that would be selected by bits 25 to 21, the base register. But one thing you said, is it A or B that gets the sign? I'm not sure what you mean by the sign.
That gets added.
That gets added, yes. Yeah, that's a base register. So maybe I'll write that down. So that's the base register, and the whole thing is the address, the base register plus the offset. Okay, now we have the address. What are we doing with the address? We have the address here. That can come around into the memory, and we're going to read the memory into the memory data register. Okay? So the MDR gets the memory of ALU out. That has to happen in the next cycle. MDR gets, am I calling it memory? Yes, it's memory of ALU out. Okay, so now we've done the reading of the data. The data that we're loading from memory is here. That gets sent to the right data of the register file. The address, if you look at our machine code, and I'm going to look at my cheat sheet, it's going to be selected by bits 20 to 16 of the instruction. So bits 20 to 16 of the instruction tell you which register to write, and the data is coming through that
So
MDR.
there's machine code and then it's
Easy enough to
decoding
write.
the instruction instead of the machine code that is. You know how to execute the code like what?
RF
It's like so we're decoding something.
20
The
to
instruction.
16 of the
It's a machine
IR
code for the computer.
gets the MDR. Now, one thing I said that I kind of lied in earlier, I said that, well, first of all, before I talk about my line, first of all, this is complete. Everybody sees that this is a load word. You got the address, you got access memory, you got the data, and you stuck the data in the register file. Now, one thing I said that I lied about, does anybody know what it is? No? Well, I said anything that you use in an instruction must be assigned in the previous cycle. Anything that you use in the cycle must be assigned in the previous cycle. Well, here I've used IR, and it's not assigned in the previous cycle. So that's an exception to the case. IR, we just assume it just sits there. Okay? I mean, the book also makes that so it's not. Of course, we could have written IR gets mem of PC in every one of these cycles, but that's kind of redundant and boring. So we don't do that. Okay. Are we ready for execute of store word? Address computation is the exact same. ALU out gets A plus sign extent of IR 15 to 0. Where is the data coming from? So store word, you need to also pick some data. The data is coming from the register file. So look at the machine code. B happens to be that data. So B is what you want to write into memory. So I want to send B the path for B is coming down here and goes into memory. That path exists. And ALU out contains the address. That path exists. So we have both the address and the data assigned to on the previous cycle. I'm going to leave an empty line here. You want to do that too. 2. Mem of ALU out gets B. Okay, the reason I left the empty line is I'm using B and I haven't brought anything into B in the previous cycle. So I want to rewrite what I did in B code for B here. So B gets RF of IR bit 20 through 16. Now I will say that I'm being a little inconsistent with the book. The book, I said IR we keep constant. The book also sometimes ignores A and B, and they don't explicitly mention what you're reading to A and B. Mainly because there's no choice. The A and B always get, there's no mux in front of them. It always gets what's coming from the register file. So you could argue that that's not. You could argue that that's not needed. However, I have found that students often make errors when they don't explicitly write it, so I'm including it. Okay. Are we ready to go on for the next one? This is really easy. Okay. Okay, now let's do branch.
I hit my eyes.
Execute for branch and equal. As usual, we will not do branch and not equal because the architecture that we have does not do branch and not equal, but it's very trivial to modify and it's not terribly exciting. Okay. Remember, in the decode phase, we already have the branch target address in ALU out. So where are we at? We have the target address in ALU out. So the only thing that we have to do is decide if A equals B. And we also have the two registers we're comparing in A and B. We just have to subtract them, check if the result is 0, and if the result is 0, we need to stick ALU out, which has the target address, zip back into the PC. If it's not 0, then we don't do anything because PC already contains PC plus 4. If A minus B equals 0, then PC gets ALU out. So that's so execute branch and equal takes 3 cycles. I'll let you do the jump because jump is almost too silly to even do. It's too trivial. Okay, so jump is something else that you can do. And now we have the complete RTL for our instruction set. I'll state again that in the real world, this would be a written in Verilog program, and given this RTL, there are tools which will automatically generate the control path from this RTL. But we are going to do it by hand because we're learning. We can't just, well, we have to learn. So now we need to talk about how do we control all these things. Yes?
In execute load word,
Yes. Let me put that up.
so there's one cycle, the first cycle puts something in ALU out.
Yes.
Okay.
Then the second cycle is putting mem of ALU out as NPR, but we didn't need to put anything into mem first.
Well, mem and register file, we're assuming that they contain values because that is your program stuck value in mem of something. This mem is memory. Your program put something into memory. Well, actually, it doesn't need to. You're reading that element of memory, whatever it is. If your program didn't put anything there, you have a bad program, but the architecture will still execute it. It's only these hidden registers, the A and B and ALUL, that we have to specify in the previous. You have to write in the previous cycle.
Kind of like a follow-up. If everything happens on like the rising edge of like a clock cycle, doesn't mem get ALU out at the rising edge, and the writing happens at that?
Okay, so that's a good question. Let's make a little diagram. So let me get rid of this. So you have a register, you have another register, you have a bunch of combinational circuits in there. Okay, so let's call this X, and let's call this Y, and let's call this Z. And I don't think it's going to matter what that is. So let's make a clock. Okay, so X, let's say this combinational circuit happens to be an incrementer, plus 1. X, let's say X is going to be 79. It's 16 bits or 32 bits or whatever. So when does the, so on the, let's see, on the rising edge, I need to make some lines to make myself straight. Okay, so let's add to the straight line as we would get. So let's say X is 79, and somewhere in here it changes to 91, and we'll finish this in a minute. So the Y is going to be since Y has no clock, it's combinational. So it's just slightly after the X changes, Y is going to change. So Y is going to be a different color. So slightly after this, I'm going to exaggerate the time a little just so it's clear. It's going to become 80.
How did you make it circle?
And it's going to stay 80 until slightly after this.
Shocker.
And then it's going to become 90.
Put it back. Put it back.
Okay. Now,
It's like a pencil, bro.
so Z on this rising edge, it's going to be 80.
You're writing off of the screen?
Thanks. So on this rising edge, it's going to become 80. Because that's what Y is. And then on the next rising edge, okay, so let's continue this. It's going to become 92. Okay, so effectively what Z did is it read X on the previous. Oh, I screwed up, didn't I? X cannot change in the middle. X is a register. I'm sorry, let's start again.
forbid I want to eat in your phone.
Mm-hmm.
Can I have a stomach ache for a week?
Sorry about that.
Close my hair with the hair. Hopefully that faded out.
So your hair is normally this black, right? Sorry, this black. What is my professor drawing, man?
What is the plus one?
Okay.
The ALU.
Plus one.
Okay, so X. Each rising edge. Oh, I guess I have to draw my lines again to make it straight.
What's the plus one?
No, bro, es incremental. It's not.
So X is going to change slightly after this rising edge.
Your fingers
So
are
it's going to
gross.
be something, whatever it is. So right after this rising
I
edge,
don't know, Mike. Oh, dang, your fingers are this full. How?
it's going to change to 68. And it's not going to change, because this is like a sequential circuit, it's not going to change again until slightly after this rising edge.
This is a loop. This is a loop.
75. And it's going to change again there, but let's not worry about it. Okay, so when does white change? There's going to be some delay. It's going to be less than a clock cycle because we designed the clock cycle to be long enough. So there's going to be some delay for the white to change after the X. So so a little after that 68, Y is going to become where's my pen go? I lost the pen somewhere. Oh, here it is. So a little after this changes, Y is going to become 69. It could be something, we don't know what. It's so Y is going to become 69. And a little after the 75, Y is going to become 76. Okay? And then when does Z change? Z changes at the next rising edge. So at every rising edge, Z is going to change. We don't know what it is here. At this rising edge, we still don't know what it is because Y is still undefined.
Oh, yeah, but JSON file is like a hash map, right?
Yeah, it's a bunch
But
of
at
objects.
this
JavaScript
pink is the
object.
rising edge. At
Is
this
it set
rising
hash
edge,
maps?
Y was 69. So
yeah, pretty much
this
there,
becomes
hash map
69
in JavaScript.
slightly after
Yes.
this
But
rising
a
edge.
hash, it's an object, but they just stay kind of similar. That makes sense.
And at this, let's say this continues. At this rising edge, it's going to become 76, slightly after this rising edge. So what did it do? So it added 1 to the X at the previous rising edge.
Right.
So so does that answer your question? So whatever was stored at the previous rising edge, because there is some minuscule delay after that rising edge, let's say 1 picosecond. And whatever stored 1 picosecond after the previous rising edge is going to get processed and stuck in the register which is outputting Z on this rising edge.
I'll have to think about it on my own.
Okay, you sure?
Yeah.
Okay.
Thank you, though.
Okay. Yeah, it's kind of the homework I was due today or last time. Well, I'll do it today. No, today was the stack. the one homework I was due last time, we had a delay in one of the circuits.
Oh, yeah.
So that circuit is processing the result from the previous cycle.
Right.
That's kind of what we're doing here too. So going back to the RTL, I think you asked an old word. So whatever was stored at the previous rising edge is now being, 1 picosecond after the previous rising edge is being read. And it's being processed and going to memory, and the result is going to the NVR.
Oh, but kind of like in the middle, the register is still outputting
Oh yeah,
LU out constantly,
Yes.
and then at the rising edge, then MDR takes it in.
yes.
Ah,
Yeah, because
okay.
because this is not, X is not changing anything.
Right,
It's always
right,
outputting
okay.
something.
That makes sense. Thank you.
I mean, don't think of output as it's actually physically doing something.
Right,
Think
right.
of it as just, it's the state of the wire coming out of it.
Right, yeah.
And that's not changing anything.
Thank you.
Yes.
Could you just repeat what you said one more time?
Pardon me?
Could you just repeat what you said one more time?
What I said then.
Oh, okay, about the,
Well, I said a lot of things.
the last bit.
The don't think part.
Little before that.
What did I tell you before that?
Use the don't think, like don't think that.
Yeah, don't. What I said is don't think
Output's
about.
not changing in between, and
Yeah.
so it's constantly outputting. It's not constantly outputting, it's in the state.
The
Right, that
Alzheimer's
state's
bit.
then
The
ready at the
Alzheimer's.
clock cycle.
The Alzheimer's.
Yeah, don't think about it as as some register doing something. The wire at the output of that register has this value on it, and it's going to stay at that value until the next rising edge, until 1 picosecond past the next rising edge. Okay, so now we have a bunch of registered. I'll just use R-type for my canonical example. So we get rid of these. So now we have a bunch of register transfer language descriptions of what an R-type instruction does. Now we have to design the control set. So before we design the control set, let me tell you a little about. Well, actually, let me just throw it up, and then I'll tell you a little about it. I'm going to hide some parts of it.
Papa John pizza.
So let's just think about fetch.
You paid a dollar for that shit.
Okay, I'm going to hide that part of it.
Tissue. Clicker, scooper, finger,
Okay, so I'm just
burger.
okay. Oh, actually, I think I should zoom in.
Cheeser.
That works. Okay, so what is the fetch doing? IR gets mem of PC. If you look at the data pad, for IR to get mem of PC, that means this mux has to be a 0 because the other option is the wrong option. So and that 0 is selected by a signal called IRD. So IRD has to be 0. So we write IRD is 0. Maybe a point there. So we write IRD equals 0. What else are we doing? We want to read memory. Let's see, memory is this one. So we want to read memory. Otherwise, we're not reading memory. Okay? So we write memread for that signal being a 1. Okay? So that gets the IR. Is that enough to get IR gets mem of PC? Mem of PC? Yes, that is. Because we're reading memory, we get the right, the correct address into this address input. Data doesn't matter for that for writing, and we read it, and the IR is going to be written. However, to actually write this IR register, we need a sort of 1 on this signal, which is called IR write. So we also write IR write. So these three signals, this one, and this one together can control the first part of the first line in that RTL. Everybody got that? Second line of that RTL, PC gets PC plus 4. What do we need to control to do that? We get PC coming into this mux. So this mux, which is ALU source A, has to be a 0. PC gets PC plus 4. This mux, which is ALU source B, has to be a 4. I'm sorry, a 1, 0, 1. And you do an add. ALU source A equals 0, ALU source B equals 0, 1, and ALU off, I'm using the figure in the book, add happens to be a 0, 0. Okay. What else? So I've controlled what's coming out of the ALU, but I have to make sure it gets written into the PC. Get it into this mux, so that means this mux, which is PC source, has to be 0, 0. And I have to make sure that the PC is actually written. That means PC write, this signal has to be a 1. Any one order, anything is 1, so I'm doing a PC write. PC write, PC source equals 0, 0. Okay, now before I go on, I want to tell you a little about how to read. This is a state machine. This is it's one. Once I uncover it, it's a state machine. Right now, it's just one state. Before I go on, I want to read it. I want to tell you how to read these because the notation is slightly different than before.
You don't want me to see?
Yeah, give me a second. Let me just write down how to read this first. This is just our conventions.
Love it. Do you have more?
I have this in another pair. The other pair says like King of the VCs or some shit. Yeah.
Fuck yeah. Should you get more silly socks?
Well, there are two types of signals. There are assertive signals, which are like things that actually do something, active, things that actually direct that you do something, like read a memory, read a register file, write a register file. And then there's the non-assertive signals. So we're going to have a different notation for the two. If an assertive signal is not mentioned, then it's implicitly 0.
I think we got time to understand this.
The non-assertive, and I'm going to tell you a little more about what exactly it is.
Thank you so much.
The
I
non-assertive
didn't understand how I have the project.
Okay. Did you do the written part?
Hmm?
Did you do the
is
written
not
part?
mentioned.
Written?
It
The
is
tape.
don't care. And just to clarify, by assertive signal,
There's more
we
than just the
mean
project.
Oh, what?
You have to make 2 tables and write a paragraph.
right,
About?
Did you even read the
and by a
instructions?
non-assertive signal, we mean the mux selects
What's the table? What do I gotta do?
ALU off code,
Okay.
And then write the time
what else?
for each one. And make a chart.
Yeah, I guess
How do I
that's
test
it.
out the, how do I test it out?
Sort of off screen.
Oh,
And make the function
Thanks.
and then
Make
test
it,
it in
test it
main.
and then test it out in my,
yeah.
in the data, right? Wait, where do I get the test? What do I
Okay,
get
so
the
that's how
test?
we're going to read the state machine. So I if the signal is not for something like a read and a write, we have to explicitly say 0 or 1. Because, well, no, I'm sorry. We have to explicitly say if we're doing the read or the write, it's a 1. Because otherwise it is assumed to be a 0. This is what we're sending to the VLSI designers. They're going to read that. If you don't mention it, they're going to interpret it as a 0. For the mux selects and things like that, if you don't mention it, they're just going to interpret it as
Did you
a
actually
don't care.
It's 43 to 50.
So now we can continue with the statement change.
Wait, so you actually did, you actually
Everybody got this? I can take this
144 to 55.
off.
by yourself.
I see some people writing, so, okay. Okay, so now we got the fetch. After the fetch, we do the decode. And the decode of this, I guess I'll do this one. I'm not going to do all of them because it's going to get really boring.
But
The
you know there was a
decode is
paragraph?
something into A, something into
You know there was
C.
a paragraph.
What goes into A and B doesn't need any control signals because there's no choice of what goes into A and B. So we don't need to write anything for that.
Well, am I
So
safe
that's
here for
part is trivial. However, for ALU out, it's PC plus this thing, shift sign extend, we do need some control signals. We get it's 15 to 0, this is coming into here, sign extend, and shifting. So we want to make sure that this mux is a 1, 1, 3. And that mux is labeled by ALU source B. So you want to make sure ALU source
So
B
is there like a
is
template that I
1,
could use for the testing?
ALU source B is 1, 1.
I have it. I think I still have
PC
the
happens
code.
to be ALU
Because
source
the
A
runtime
0.
for
I
you and
will
for me is
show
going to be
you.
different.
It's
Obviously,
the
I'm
main.
look it up.
Did
And
I send you
ALU
a main
off
file?
is a plus. If an 0, 0 happens to be a plus.
But the runtime is going to be different.
Yeah.
That's why.
So we got the decode, and we make an and this is we make an arrow from this state to this state. Now, after this, the next state it depends on your instruction. Fortunately, our instruction has been loaded into the IR, so
We're
we
just
can
gonna
look
turn
at the
it in without
instruction
no
and
video.
figure out what the
To be
next
fair,
state is
I
going to
changed
be.
it. I changed it.
And there's this field in the instruction which
What do you
says
mean?
you can
I changed
decode
it.
and figure out is this a load word, is this a
And I
store
changed
word, is
like
it an archetype,
some
is it,
stuff the way you did
whatever.
it into like how I
And
would
when
do
you do
it.
that, you
In
get
terms of like
4
syntax.
possibilities. I guess I don't need to show
But
this
what are you changing about the syntax?
anymore.
For
You get 4 possibilities. So depending on whether the off field is a load word, store word, archetype, branch, or jump, we go into one of these 4 states. And let's see, I don't want to do
Oh, say
all of
that's
these,
cheating
but
on
let's
Steven.
do this one's most interesting. Let's do the store word.
That's crazy. I'm telling Steven.
Which implicitly also does the load word, does part of the load word. So the first cycle of the load word and store word, you're getting an ALU out, adding these 2, A plus a sign extended immediate. That means A, ALU source A has to be a 1, B, the sign extend immediate is 2. So ALU source A is 1, ALU source B is 1, 0. And you're doing an add, 0, 0. Okay, I said I'm going to do store word. So now at this point, cycle 2 of the execute, depending on whether I have a load word or a store word, is going to be different. The B comes for free because there's no choice. So depending on whether it's a load word or a store word, I'm either going to get something into the MDR or I'm going to stick something in memory. Let's do store word. So mem of ALU out gets B. It's the cycle 2. Mem of ALU out is, has something. So you want this mux to be a 1. You want to do a write memory. And the data is coming from B, so that's fine. So you want to do a write memory with this mux, which is called IRD being a 1. Well, you know, memwrite IRD equals 1. And we do it for all the instructions. Let's not bore ourselves too much. When we do it for all the instructions, we end up with this state machine. One thing to be very careful about, we need to make sure that we move back to the fetch. If we haven't done that, then we basically we have a dead end and we put our machine into a halt, which is not a good idea. To make sure, we basically crash the CPU. So at the end of every instruction, we branch it back into the fetch for the next instruction.
Good time.
Question?
Yeah, Hunter.
Because you mean the first cycle? Because we're adding the immediate sign extended immediate and a base register, and the addition is represented by 0, 0.
Okay, so what if it was like subtract?
Well, we're not doing a subtract for store word. For an R type, let's see, where's R type? R type is here. ALU op, which we call op in the single cycle, is a 1, 0.
Okay.
And for branch, which is a subtract, ALU op is a 0, 1. Yeah, somebody said they would ask a question, and I said ask me later. Did I answer that, or did you still have a question?
Yeah.
That was you?
Yeah.
Okay. I forgot about you, sorry. Yeah.
Why are memorize memory and others assigned 1?
Why are,
Memorize, for example, why is it assigned 1?
well, because when we say, remember, an assertive signal is not mentioned as a 0, so when you say it, it's implicitly a 1. So for reads and writes, when we say it, that means it's a 1. So that means IR writes is 1, memread is a 1, memwrite is a 1, and so on. That's a notation. But it is standard notation. It's not kind of same pattern stuff. Because it's an active thing that you're doing. So when you say it, you're doing it. It's not something you're picking a choice. Yes.
Could you briefly walk through store word just one more time in this diagram?
Okay. So store word. So I assume you're not asking about fetch and decode.
No.
So after fetch and decode, first cycle you're doing an addition of the base register, which happens to be an A,
Why should I start applying for some
the
internship
immediate
next
sign
year?
extended.
When is internship? When is it?
Okay. How do we do that? We look at our data path, and we say we have A, that means this box has to
We'll
be
just start like May. Like I have Walmart.
0, 1. ALU source A. I'm sorry, not 0, 1. ALU source A is a 1.
June, July, August.
And sign extended immediate, ALU source B is a 1, 0.
When do you usually get like the? When do you know if
ALU
you're accepted or not?
source A is a 1.
Not sure.
ALU source B is a
When
1,
do you
0.
get like?
And we're doing an
When do
add.
they tell you if you're accepted?
And that's exactly what the RTL does.
I mean, it's gonna depend from company to company. Like I Google, it's like
So that is the
because they have so many rules.
first cycle of the RTL.
For
The
me,
second cycle of the RTL
actually, I
is
applied to
mem of
Goldman,
ALU
but I
out
was
gets
like,
B.
I didn't get my offer until like the end of October. So
B? Oh, that's
August,
already
September,
going
October.
there. ALU
Oh,
out.
really? You get the offer
You
in
have to
October?
make sure this mux
Yeah, the very
selects
end.
1, and that's the IRD mux. And you have to make sure we're doing the mem right. So, where's my state sheet? So mem right and IRD equals 1. And then we go back to fetch.
Well, how many interview did you do?
To answer your question?
And then there was the online assessment.
Okay, so now we can do the
Just
same thing we did
waiting for us to
earlier
talk
for
about
single
recording.
cycle,
Yeah,
and
one was like a
we
recording,
can
and
now
one like OOP
change,
slash system design.
make new
One was- the other one was it?
instructions,
The other one was like OOP slash system design.
which is obviously what we're gonna do.
That was not too bad.
Okay, so
For me,
that,
it was literally
so
just
I
like
guess
how would you design
today was
this
the
and
first
go
single
from there.
cycle homework. You will have the second single cycle homework due on the Monday after break, and the first, the simple, the first single cycle is easy, the second single cycle will be harder. And similarly, the first multi-cycle will be easy, that'll be due the Wednesday after break, And the second multi-cycle, which will be a little more interesting, will be to the following Monday. Okay, any questions on other topics before we go on? Yes.
When are we gonna get the homework, that's due, after break?
Pardon me?
When are we gonna get assigned the homework?
Probably on Friday or Saturday. You have a whole week to do it. Yeah.
Question about the register file, so what's the difference between the right data and the right register?
Okay, the right data is the data that is getting written. The right register is a 5-bit field which is telling you which register you're writing. I'm writing register 17 with the number FF04648. It's the same with the memory. The data is the data that gets written, and the address is the address. Except in the memory case, both of them happen to be 32 bits because memory is 2 to the 32 bytes. Well, in the register case, there are only 32 registers, so one of them is 5 bits. Okay. You know what? Let's quit really early today, and because I don't think I have enough
Okay.
time